assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So in this problem, we have this bar of charge down here along, say, the x-axis, and we're asked to find the voltage at a point P above the center of the bar, and that's a distance d above the center of the bar. And so we're actually given two cases. One case when there's uniform positive charge along all of this, and then one case when there's one half is positive charge and the other half is negative charge. In both cases, the bar is 6 centimeters long, and the charge density is 3.68 picocoulombs per meter. So that's the charge density along here. In the first case, it's all positive. In the second case, it's positive on one half and negative on the other half. Again, we're told to take the voltage at infinity to be 0, and the distance d from the rod is 8 centimeters. So basically, this just comes down to a calculus problem. And I'm not going to go through all the calculus in detail. I'm assuming that you can do that on your own. So we can say, well, the voltage, you can think about each little particle, each little segment of charge here adds up to the total voltage here. So we get a voltage from each little segment of charge. So the differential voltage from that segment of charge is just, dq over 4 pi epsilon naught r, or this is 1 over this is k. So we write this k dq over r if we wanted to. Now, what is r? Well, r is the distance from that little segment of charge to point P. So wherever we are here, we're at some distance x along the x direction, and we're always at a constant distance d in the y direction. So the distance here, r, is the square root of d squared plus x squared. And then because we have a charge density, the charge here is just the charge density times the differential length over which that charge density acted, x. So we can substitute our differential charge, and now we get a differential length. So substituting all this stuff in and pulling out the things that are constant, we basically see we just need to do this integral. Okay? And that integral, so the integral here, the indefinite integral is given by here, and then we need to evaluate it at the limits. So we're integrating x with 0 at the middle, so we're going from minus L over 2 to L over 2. So we can plug those in and do a little rearranging with our natural log, meaning natural log of a minus natural log of b is natural log of a over b. Okay, so we can make that substitution and make that simplification, and then we get this voltage here. You can see here the expression for it is given by this expression. So what can we say? Again, doing this all symbolically allows you to look at some things. Obviously, the voltage is proportional to the charge density. Okay. Which I guess I just called lambda here. I guess we should maybe just say this equals to lambda. So this charge density here. That makes sense. As the charge density goes up, the total charge is going to go up, and that means the voltage at P is going to go up. Now, if we look at this natural log term, let's say D is 0. If D is 0, then this is 0, and then the denominator is infinite, right? And so what we have is the natural log. When is the natural log? And this would be this would go to infinity. This would be positive. So again, we'd have an infinite voltage here. I think, yeah, because this would go to positive. The natural log. When is the natural log positive infinity? At infinity. Now, if let's see here. I'm not sure what else we can really say. As D increases, it's hard to look at what happens with D. We'd expect the voltage to go down, and you could then plot this and see that in fact that's what happens. as D gets much, much larger than R, or L, if D gets a very much larger than L, then this dominates this, and then we'd have 2D here, and that would dominate this, and we'd wind up with 1 here. So the natural log of 1 is 0. So if D were, again, so basically that's what we're saying here, is that as D goes to infinity, the voltage goes to 0. Okay, so as the distance we get from this point goes up to... So that all makes sense. And if we plug in all our values, what we have, we get 24.3 millivolts is the potential there. Now, in the second case, we can either, go through and do this integral again. Again, now we have to divide it up because part of it has a positive charge distribution, positive charge, and part of it has a negative charge. So we can divide it up, but what we can also see is just by symmetry that we'd expect that the voltage here should be 0. And if we divide up these integrals, again, we can see that this integral should equal to this integral because of the even function, right? It's an even function of x. So whether we integrate from minus L over 2 to 0 or 0 to L over 2, we should have the same area under those curves. So in fact, you can go through the calculus and do it. And in fact, this turns out to be 0. And again, you should expect that just because of the symmetry here. The two charges basically, cancel each other out as far as the voltage that they generate.